Saataiskohan me tässä vaiheessa yhteys Sabrina Maniscalcoon? Me ollaan ihan muutama minuutti etuajassa, mutta ehkä se onnistuu.
Hi, can you hear me?
Hello, welcome to our session on physics. And we have the information which is distributed to the audience that you are a physics professor in Helsingin Yliopisto and you are active in quantum mechanics theory, for instance, decoherence, if I can pronounce it. And also
Yes.
with quantum computation questions. Also, it's mentioned in the description that you operate in mind and matter area together with other like humanistic and social scientists. And before this, you have worked in Turku University and quite recently moved to Helsinki. So the floor is yours, please.
That is correct. Thank you very much for the nice introduction. And of course, thank you for inviting me to present or to talk something related to my research. I will begin by sharing the screen with my presentation. I hope to be able to do it soon. You should be now seeing the title of my talk, The Quantum Technology Revolution. As you correctly pointed out, this is also my field of research. I work in quantum science and technology, and I am the Vice Director of the Center of Excellence for Quantum Technologies, funded by the Academy of Finland, as well as Vice Director for Institute 2, which is our national umbrella, both of them involving University of Helsinki, Aalto, and VTT, handling anything related to this, what we call as the second quantum revolution. So I want to talk to you a little bit about that. This is briefly the outline of my talk. I will talk about quantum computers, what quantum computers are, what they are good for, and then I will focus a little bit on an application of quantum computers that is specifically tailored in the life sciences. And I would like to conclude with a few remarks on the importance of quantum physics, and in particular of education of quantum physics for the general public, not just for experts. So let me begin with the definition or with a few words about quantum computers. And in fact, I will begin by telling you what quantum computers are not. Sometimes you may read in the media that quantum computers are like computers, but faster and more powerful. And this is an example of misinformation. This is not really as they are, or how it is not really their most important defining trait, I would like to say. The most important thing to have in mind when thinking about a quantum computer is that they use completely different modality of computation, and this comes from the properties of their individual constituents. Quantum computers work by manipulating microscopic quantum particles that form inherently the quantum chips, okay? And these quantum particles work according to laws of quantum physics that are very different from the laws of conventional physics. And therefore, the logic, the way of handling them, the way of programming them is completely different. It requires really to shift our whole knowledge when it comes to computers, incorporating advances in quantum physics. And this is the extraordinary achievement that is happening right now. For the reason I just mentioned, quantum computers will not replace conventional computers. They will not replace the laptop I'm using now to talk with you, but they will accompany them. So the reason is that quantum computers are only useful for certain problems which are difficult to solve. And when I say difficult, I mean impossible for all practical purposes to solve on conventional computers, okay? And when I talk about conventional computers, it's not just my laptop, it's also any supercomputer, say Lumi. Nowadays, Finland is hosting this high-performance supercomputer. Any conventional supercomputers. So they will, only for certain tasks, they are able to break the boundaries of what can be computed, not in general. So they will not replace, they will accompany. Another point that I like to stress is that quantum computers without good algorithms are useless machines. There is a race nowadays to develop quantum computers and quantum hardware. Not only giant companies like IBM, Google, Intel, Microsoft are really investing sensibly in these directions. Also startup companies, including in Finland, several achievements related to the building of the hardware. But the hardware is not enough. Precisely because of what I said before, the hardware alone will not allow to use the software that has been developed, will not be possible to use it with the software that has been developed for conventional computers. And therefore, we need to, at the same time, as the development of the hardware progress, we need to develop the software. Now, when it comes to what they are good for, once again, I would like to use the same, so to say, trick I used before. I will tell you what they are not actually good for. Okay, this means that, to be precise, what people think might be good for, but actually it is a long way along the road. And I will refer to a podcast. If you like podcasts, I would really recommend. It's called, you can find it to this link. It's called preposterousuniverse.com. This is the podcast number 153, where a very well-known physicist, Sean Carroll, interviews John Preskill. John Preskill is one of the founders of quantum information theory. And then really, he interviews him on the topic, what are quantum computers useful for? Now, the main range of applicability of quantum computers are simulations. So quantum computers are really tailor-made for simulating the behavior of other quantum systems, like molecules and materials. So they are naturally apt to simulate, for example, molecules that can be used for drug development or for simulate new materials, because the systems themselves are quantum. So you exploit a quantum system to emulate another quantum system. Whether or not they will lead to breakthrough in cryptography or maybe in optimization problems is less clear. And the reason why I point out this is that in the media, one of the first message that is generally given is that quantum computers are a threat for security because they can break encryption codes. So this is one of the most commonly referred to use of quantum computers, and perhaps one of the most scary ones, because we do know that all our governments and many institutions, they use cryptography in order to protect data. So is it really true that quantum computers are a threat now because they could break a cryptographic code? It doesn't seem really to be something we have to worry about, not just because of the existence of post-cryptography techniques, so techniques that would be for encrypting data that would be resistant also to quantum computers, but also because the use of quantum computers to break cryptographic code is very, very far ahead the line. It is absolutely not clear when and if it will be possible. And there has been recently a publication that is precisely showing how, for example, what would be the requirement to factor, also to break, I will not go into the details, but to break a cryptographic code that is commonly used to protect data in a reasonable time, say in 8 hours. And the number of quantum bits, fundamental units of information in the quantum world that would be necessary are over 20 millions. And I just would like to tell you that at the moment, the most advanced quantum computers we have contain 65. from 65 to 20 millions is not just a technology advancement, it's really a lot of fundamental research along the way. So certainly, if you read that quantum computers are something for which we should be scared because of cryptographic reasons, you now should have in mind that perhaps this is not the most short-term issue or concern. Now, going back instead to a more concrete applications, I was already mentioning before the fact that we can use quantum computers to simulate other systems, in particular to simulate molecules. And the reason of this is that very often molecules that can be used like new molecular entities for drug discovery, they are found they are in highly correlated states, and highly correlated states, or some states which possess inherently some quantum properties, are very hard to simulate on conventional computers. And this is one of the reasons why in the drug development and discovery, research and development, there is an issue now, because really it is very hard to simulate using computers molecules that could be good candidates for drugs, and therefore when going through clinical trials, a lot of new molecular candidates they fail. So one has to restart the whole process for identifying the new molecular entities. So quantum computers may be of great help, and a lot of companies and a lot of startups and a lot of universities are working in this direction. It is believed that they may revolutionize life sciences, exploiting their ability to emulate other quantum systems. This is something that we are also doing within my startup, a startup company that I have recently co-founded, and the name is Algorithmic, and which is precisely aimed at exploring this direction. So we are a group of scientists that are going in the direction of trying to understand whether and in which way quantum simulation, noisy quantum simulations, quantum computers that already exist, would be an alternative, or rather than an alternative, could be used together with classical conventional computers to improve the development and the discovery of drugs. And in particular, the main areas would be develop new and more effective drugs. But in general, there are a number of conversations that we are having with healthcare institutions and with pharma companies, for which it seems that it would be very important to identify problems that exist in the pipeline and that would be efficiently solved and addressed by exploiting the quantum properties. So quantum chemistry is definitely one of the short-term domains of applicability. And what is interesting, however, in the framework of quantum chemistry, of simulating of molecules, is that the most successful strategies combine classical, and with classical I mean machine learning, optimization, AI, with quantum algorithms. So it's using the combination of the two that it is possible to achieve the highest advantage and to exploit in the best possible way the quantum resources. And for this, we have been recently undertaking a collaboration with IBM, which has led to a new algorithm to extract information from a quantum computer for quantum chemistry simulation in a faster and smarter way. And I will not go in the details of this result, but what I would like to point out is that I think something which is at the very core of quantum devices is the ability to extract information from the quantum computer in a very skillful way without destroying the information that you extract. This is because the quantum system contrarily to conventional classical system, are very strongly perturbed by any measurement or observation. So this is currently a very important bottleneck in the development of quantum algorithms that work on realistic devices. So to find ways to extract information faster and in a smarter way seems to be the most promising direction in order to fully unlock the potential of near-term quantum computers. And as I said, importantly, this should not be done without neglecting the enormous advances that currently are going on in the field of AI, but rather combining it. Now, I would like now to summarize what I just mentioned before and go towards a conclusion, although the last part for me is specifically important and crucial. Now, we are in the process of contributing to the emergence of a new ecosystem that exploits the power of quantum physics to unlock new modalities of computation, of simulation, of metrology, and of sensing. And in order to do this, definitely we need to support fundamental research which happens in the universities. We need to support startups that are more, let's say, focusing of collaborations also with other companies, but to the realization of much more practical and short-term industrial achievements. So in this moment, really what everybody is trying to find or to identify is industrially relevant use cases for quantum computers and quantum simulations. And this is what, I mean, clearly needs to be supported and encouraged at this point. But also, importantly, we need to educate the general public and educate the policymakers, educate the executives of big companies who are ready to, who are starting to become quantum ready, about a technology which has a very strong disruptive power. How do we do this? Our direction was to develop an online platform. It's called the qplaylearn.com, which is open and accessible to everyone and contains multimedia resources aimed at teaching in some way quantum science and technology in a playful way. So this is aimed at the general public, but it is also aimed at high school students and quantum enthusiasts, at university students, and at company in the framework of retraining for employees and executives. Obviously, the tools that we are developing are tools that are developed in collaboration with physics educators, but also in listening to the needs of companies, to the needs of lecturers in universities, and to the needs of high school teachers and lecturers. The reason why we do so is because we really deeply believe in the importance of science education and scientific literacy for our society, and therefore we think that our society needs to be ready for the quantum technology revolution. And it is really our mission as qplaylearn to provide multi-level education, which is targeted to the different audiences on quantum science and technology, regardless of the age and background of the audience. Obviously, it is adapted to the different levels, to the different needs, to the different previous knowledge. We believe that really everyone can understand the beauty of quantum physics and the power of quantum technologies without necessarily becoming an expert on quantum physics, on quantum science and technologies. And we believe also that in order to achieve this goal, it is important to develop a new method which includes different medias, including video games, as you will see from qplaylearn, in order to understand the quantum work in a way that is fun and visionary. Most importantly, we believe that if we want to reach a general public, we have to understand that as science has now confirmed, intelligence is diverse. We learn and we think differently. Some people use more logical intelligence, others have more kinesthetic intelligence, other people think more visually. So we have to open up our way of explaining and teaching to include these different types of intelligences. And because of this, we developed an approach which uses three different techniques: play, discover, and learn. In play, we use video games, videos, and experiences to build intuition on quantum physics. In discover, we use the physics experiments and physical concepts really to help the mind to conceptualize physical phenomena. And then in learn, we introduce mathematics, and therefore this is the part in which a more abstract and formal knowledge is developed. And of course, everyone can start from the level one wants or is more familiar to, and then explore the others. QPlay Learn is aimed at building connections between academia, companies, schools, and citizens. So it's a collector of material, which is then reorganized and scrutinized by quantum scientists. And is aimed at high schools in order to
1 minute, please.
Yes, in order to engage the students with online games. It is aimed at university in order to enrich the class with multimedia material. And it is aimed at companies in order to speed up the learning process of the teams with a new and innovative approach. We have developed, in this case, Inspiration Quantum, that is a course for teaching how to distinguish hype on quantum computing from something that is more close to the truth when reading the media. And this is everything I wanted to tell you. I'm glad to, if you have questions, and I thank you for your attention.